Okay, and let me share my screen. Okay. All right, so I'm going to start off with chapter 8, which is a natural follow from chapter 7. If you recall, the last thing we discussed in chapter 7 were the quantum numbers, the 4 quantum numbers for electrons in an atom. And here we're going to see how that leads to our understanding or modern understanding of how the electrons are arranged in an atom, all right? So when we talk about that type of arrangement, we're talking about the electronic configurations, all right? And then after that, we will see the connection between this the electronic configuration of an atom and how it relates to the atomic properties, and also how it can explain the positions of different elements in the periodic table. So all of these things will be discussed in this chapter. All right, so let's talk about the multi-electron atom as opposed to a single electron atom. In the case of the model that we were talking about in the previous chapter, what you're going to find is that in the single electron atom, namely the hydrogen atom or similar structures, you'll find that we can easily predict the energies of the different subshells and the shells within the atom. And that's because basically in a single electron atom, you have only one electron. You don't have any other electrons that would interfere with it, and therefore there'll be no electron-electron repulsion in those situations. In the multi-electron atom situation, things are a bit more complicated because of the fact that you have more than one electron, and therefore because electrons are negatively charged, they will repel each other, and therefore they can have some influence on how the electrons are arranged in the atom. So if you look at the single electron atom, hydrogen, if you look at how the shells are arranged, basically it's very simple. The first shell will have the lowest energy, then the second shell, then the third shell, then the fourth shell, and so on, right? Very simple. And the energy of each shell can be calculated based on this equation. If you recall, we saw this equation earlier. We call this the Rydberg equation, and it's very simple. This is actually based on the Bohr model, but it turns out that it is also useful for calculating the energies of the different sublevels or the different energy levels in a one electron atom, all right? So that's what happens in the case of hydrogen atom or other structures where there's only one electron. Now, when you have a multi-electron atom situation, you're going to see that things are a bit more complicated. So to show you this, we have these two side-by-side comparisons between the hydrogen atom, right? This is basically the distribution of the energy levels within the hydrogen atom, and you have the typical multi-electron atom, right? So as we said before, you have the first shell, second shell, third shell, fourth shell, and what you'll notice within each shell, where you have different subshells, you'll see that the subshells have the same energy. So you have the 2s subshells and the 2p subshells, they have the same energy. The same is true for these subshells here, 3s, 3p, 3d, and then same thing for 4s, 4p, 4d, 4f, and so on and so forth, right? So that is, very simple, not complicated situation when it comes to the hydrogen atom. What you'll find is that in the case of a multi-electron atom, things are different. For one, what you'll find is that the energy of the shells will be lower compared to that of the hydrogen atom. So for example, the first shell is here, right? And you'll notice that in the multi-electron atom, it's way down here, right? The second shell is here. In the case of the multi-electron atom, it's way down here, all right? So that's one difference between the multi-electron atom and the hydrogen atom. Another important difference is that whereas in the case of the hydrogen atom, where you have more than one subshells present per shell, their energies will be the same. In the case of the multi-electron atom, that is different. What you'll find is that there's a breakdown in what we call the degeneracy of the subshell. Basically what that means is that the energy of the subshells will be different. So the 2s subshells here would be low in energy slightly compared to the 2p subshells. And then when you get to the third shell, the 3s subshell will be low in energy compared to the 3p, which in turn will be low in energy compared to the 3d. and then you see a similar situation for the 4s subshell. All right, so that's basically the big difference between a typical multi-electron atom and a hydrogen atom. All right, and what you'll find is that in the multi-electron atom, where you have the different subshells existing, what you'll find is that the order of energy of the subshells is shown here. The s orbitals or the s subshell will have a lower energy compared to the p subshell, which would have a lower energy compared to the d, which in turn will be of a lower energy compared to the f subshell. So those are the differences between the subshells, all right, in terms of their energies, where they exist within the same shell, all right? Okay, so let me see here. I think I made mention of this point already. The orbital energies are lower in the multi-electron atoms compared to the hydrogen atom, right? So if you take the 2s orbital, its energy would be here. In the 2s orbital, in the multi-electron atom, its energy is lower, all right? It says here that in higher numbered principal shells of multi-electron atoms, some subshells of the different principal shells have nearly identical energies. And what they're referring to is basically the lowest orbital or the lowest subshell of the 4th shell and the highest subshell of the 3rd shell, right? You see that the energies of the 4s subshell is almost the same as that of the 3d subshells, right? So you might have some overlap, in other words, between subshells of different shells, all right? Okay, so this brings us now to a discussion of the electron configurations, right? So, excuse me, when we're talking about electron configurations, whenever you see this term, what we're talking about is basically how the electrons are distributed among the subshells and the orbitals that are present within those subshells, all right? So that's basically what we mean by electron configuration. And we have to use certain symbols to represent the distribution of these electrons among the subshells and among the orbitals. Now, one way of representing it is called the SPDF notation, right? And basically what this system uses are numbers to indicate the principal shell and letters to identify the subshell. And you have a superscript numbers which indicates the number of electrons that are located within the particular subshell. So for example, if you see something like this, right? The 1 here represents the shell, right? The S here represents the subshell for which L is equal to 0, which is the subshell quantum number. And the 2 here, which is written as a superscript, is basically indicating the number of electrons within that subshell. So basically the way we would interpret this symbolism here is that the first shell, which has only the s orbitals present or the s subshell present, have a total of 2 electrons within that subshell, all right? So that's basically how you'd interpret a symbolism of this type, all right? And this will become important when we talk about electron configurations of atoms. Another way of representing how the electrons are distributed among the orbitals is by using what is called an orbital diagram, or in some textbooks, I think they call it electrons in boxes. And basically what this is representing, each box represents a separate orbital, right? So you have a 1s orbital here, 2s orbital here, and you have 3 2p orbitals over here, right? And the arrows represents the electrons that are occupying the orbitals. And you'll notice that the arrows, when they occupy the same orbital, they're pointing in different directions. One is pointing up, one is pointing down. And this is indicative of the spin quantum numbers that we were talking about in the previous chapter. And the convention that is accepted when it comes to this representation is that the electrons or the arrows that are pointing up represents the electrons for which the spin is, the ms value is plus half, and the electrons that are pointing down represents the ms values, the electron with ms values minus half, all right? So that's basically another way, this here basically is another way of representing how the electrons are distributed among the orbitals. Okay, so as stated here, each box has arrows representing electron spins, and the opposing spins are paired together. We're going to talk about this very shortly when we get to Pauli's exclusion principle. Okay, so let's talk about the rules for electron configurations, right? So the first rule here says electrons will occupy the lowest available energy orbitals in the ground state configuration. Now remember, the ground state configuration is the most stable configuration for the electron arrangements in an atom. So what this statement is saying is that in the ground state configuration, which is the most stable state, the electrons will try to occupy the lowest available energy orbitals. Now, here's an example of a violation of that statement. And the reason why is because you'll notice in this arrangement, you have two electrons occupying the same orbital. Now, we know that electrons are basically negative, and therefore they will repel each other. So this would not be the most stable arrangement. The most stable arrangement would be where, where this electron here, let me just cross that out, would occupy this position right here, right? So therefore you have the three electrons occupying separate orbitals. They won't be repelling each other in that kind of situation. And therefore this would be a more stable ground state configuration for this particular arrangement, all right? So let's talk about Pauli's exclusion principle. And basically that principle is related to what I said earlier about situations like this, where you have two electrons occupying the same orbital. So what this principle says is that no two electrons in the same atom may have the same set of 4 quantum numbers, all right? So the result of that principle is that each orbital can only have a maximum of 2 electrons, and when they do so, when they both occupy the same orbital, then the spins must be opposed. In other words, they must be spinning in opposite direction. All right, so basically, if you apply Pauli's exclusion principle, you'll see that for one electron here, right, n is equal to 1, and since it's an s orbital, L is equal to 0, and there's one value of ms, which would be, ml, which would be 0, but ms here for this electron is equal to plus half, right? So that's for this electron right here. Now for the other electron, the n value would be the same, n is equal to 1. The L value would be the same, L is equal to 0. The ML value would be the same, ML is equal to 0. But because the electron is spinning in the opposite direction, then the MS value would be equal to plus half, right? So even though both electrons are occupying the same orbital, they both don't have the same number or the same set of 4 quantum numbers. They share the same n value, the L value will be the same, and the ML value, but the MS value will not be the same for both of them. So this will be minus half. I made a mistake here. Let me just cross this out. This will be minus half, all right? So basically that's what Pauli's exclusion principle is saying. No two electrons in any atom can have the same set of 4 quantum numbers. And the consequence of that is that when both electrons are sharing the same orbital, that means that they must be spinning in opposite directions so that they have different MS values. Okay, let me move on to the next slide, which continues our discussion of the rules for electron configuration. And this one has to do with how the electrons are distributed. And I alluded to this before. And this is in particular in reference to a set of orbitals that have equal energies, such as the 3 2p orbitals here. It says here, for orbitals of identical energy, electrons enter empty orbitals whenever possible. So basically, and this is Hund's rule, by the way, right? Hund's rule basically predicts that if you have a set of orbitals of equal energy, the electrons will enter each of them separately. So again, as I said before, the correct electron configuration would have this electron not here, but here, right? The electrons would rather spread out among a set of orbitals of equal energy before pairing up, all right? So basically that's what Hund's rule is saying, and that will become important when it comes to determining the electron configuration of pretty much any atom, all right? So as stated here, and this goes back to what we were saying no, actually not. This is a part of Hund's rule. Basically, when you have this situation, electrons in half-filled orbitals must have parallel spins. So if you have them in half-filled, if you have the set of p orbitals half-filled here, then the electrons, all of them must be spinning in the same direction. So this would be incorrect, all right? This would be incorrect. Instead, what you must have is this, all right? Just like we have up here, all right? So that's basically what Hund's rule is all about. Okay, continuing. So this is basically a summary of all the orbitals, all the subshells, and the capacity in each of them. And again, this will become important when it comes to determining the electron configuration. So here we have the n values. So that's the first, second, third, and fourth shell. If we look at the first shell, there's only one L value, which means that there's only one subshell, which is the S subshell. And there's only one orbital within that subshell. And the maximum capacity, of course, as far as that subshell is concerned, is 2. And therefore, the maximum capacity of that shell will be 2. And then in the case of the second shell, you have 2 L values, 0 and 1. The subshell designation in that case would be S for the 0, P for the 1. And in terms of the number of orbitals that are present, you have 1 S orbital and 3 P orbitals. The maximum capacity, remember, each orbital can have a maximum of 2. So therefore, within the S subshell, there's a maximum capacity of 2. Within the P subshell, there are 3 of them, so the maximum capacity is 6. And therefore, the total capacity of that shell will be 8. And if you understand what I just described for n equal 1 and 2, then you should be able to appreciate what happens here and what happens here, right? And that continues, of course, to literally infinity. Okay, so let's talk about how do we determine the orders of the orbitals in an atom. Because what you'll find is that as the atom gets larger, as you have more electrons present, it becomes more difficult to predict the order of the energy of the subshells. So this diagram that you're looking at as a screen, on the screen is basically a diagram that will help you to determine the order of the subshells, right? Basically, when I was a student, what I would do in order to memorize this is that I would start to the left and write down 1s, 2s, 3s, all the way down to 7s. And then I start at the second shell here, start with 2p, and I start from 2p all the way down to 7p. And then I start at the third shell where we have 3d here, all the way down to 6d. And then at the fourth shell, we have 4f, 5f, and then I'll draw the arrows as you can see here. And basically the order of the subshells would basically follow the direction of the arrows, starting from the top here, and we're going from tail to head. So the first lowest energy subshell would be the 1s, then the 2s, then the 2p, 3s, then the 3p, 4s, then the 3d, 4p, 5s, then 4d, 5p, 6s, and so on and so forth. So this is what you're going to use to help you to determine the order of the orbitals within an atom. And that will be important as well when it comes to determining the electron configuration of an atom. So as stated here, as I stated earlier, this would be the order based on following the direction of the arrows from tail to head, right? And of course, these numbers here, the subscript represents the numbers of electrons maximum that would be present in each subshell, all right? Okay, so let's get to the Aufbau principle, which is basically, Aufbau is a German word, which basically means building up. So what we're talking about there in terms of the principle is how do we build up, or how do we, add electrons to an atom for a particular element. So we're going to start from the simplest element, which is hydrogen, and then we'll move up. So hydrogen has only 1 electron, and that electron will go into the lowest sublevel, which is the 1s sublevel. So therefore, the electronic configuration is 1s, right, for hydrogen, right? The next element has 2 electrons. So basically, to get from hydrogen to helium, all we have to do is add 1 electron to the structure, and that electron will join the first electron in the 1s sublevel. So therefore, the electronic configuration of hydrogen is 1s2. So the next element is lithium. So to get from helium to lithium, we add 1 electron to the lithium atom. However, the 1s sublevel is already full because it has a maximum capacity of 2 electrons, which means that the next electron that is added will go into the next higher subshell, which would be the 2s subshell. So therefore, the electronic configuration of lithium is 1s2, 2s1, all right? Now, let me stick a pin here and talk about what we call the abbreviated electron configuration. Now, the configuration that we have talked about here before, we call them the unabbreviated version, or we simply call them the full electron configuration, all right? Now, the abbreviated version is used especially for larger atoms, but I'm going to use it. I'm going to show you how you determine it for lithium in this case. Now, in the case of lithium, the electronic configuration, as we said before, is this. Whoops. 1s2, 2s1. Now, if you look at this configuration closely, you'll see that this part here, the 1s2, has the same configuration as the group 8 element that precedes lithium in the periodic table, which is helium. So basically, to get the abbreviated version, what we do is replace the 1s2 here with the symbol for helium in square parentheses, right? So this basically is the same thing as 1s2, all right? And then we write down what is left after that, which is a 2s1, and that goes here. So this here is the abbreviated version, right? While this here is the full electron configuration, all right? So basically, to get from the full configuration to the abbreviated version, what we do is that we identify the part of the full configuration which has the same electron configuration as the group 8 element that precedes the particular element. In this case, the element is lithium, so therefore we're talking about the helium atom which precedes it, right? And we take that part which looks like helium and replace it with the symbol for helium in square parentheses. Now, in this case, it doesn't make a difference really in terms of the length of the symbols that are used in going from the full electron configuration to the abbreviated version, but it can make a difference when it comes to larger atoms, such as in the case of carbon, for example. So in the case of carbon, right, well, this is the full electron configuration of carbon, right? The 2 electrons first will go here. Well, firstly, the atomic number is 6. So the first 2 electrons will go here, the second 2 electrons will go here, and the remaining electrons will go into the 2p subshell, right? And this is the electron in box representation of the electron configuration of carbon. So to get from here to the abbreviated version, we identify the group 8 element that comes before carbon, which again is helium. And this is the electronic configuration of helium, which is a part of the full electron configuration of carbon. And we simply replace that with the symbol for helium, and then we write down the rest, 2s2, 2p2, all right, which you can see here, all right? And that's basically how that is done, all right? Okay, and then if you look at the next element, it's the same idea. In fact, to get from carbon to nitrogen, we simply add 1 electron here, and that electron will add to the 2p sublevel, and more specifically, is going to be added to the vacant p orbital that was here. So you're going to have the 3 electrons spread out among the 2p sublevel in the separate orbitals. This is a full electron configuration, and again, this would be the abbreviated version, all right? So that's basically how we get the abbreviated version, the full configuration from the atomic number, and also the electron in box notation, as you can see in the middle. Okay, the next element is oxygen. To get from nitrogen to oxygen, we add 1 electron. That electron will go into the 2p sublevel, and more specifically, what that means is that over here, the electron that is added can be added to any one of these 3 2p orbitals, but it must be spinning in the opposite direction to the electron that was already occupying the 2p orbitals. So that's what we get here in this case, right? And over here we have, excuse me, the abbreviated electron configuration. And then the next element is fluorine. To get from oxygen to fluorine, we'd add an electron to the 2p sublevel. This would be the result, which means that the electron could be added to this or this. Excuse me, the result is this here. And this would be the abbreviated version of the electron configuration of fluorine, all right? And then when we get to neon, we add an electron to the 2p sublevel, which means that the electron will be added to this orbital here, spinning in the opposite direction of the electron that was there before. And we end up with this here, and this will be the abbreviated electron configuration, all right? So what I've just gone through is basically how we get from one atom to the other in terms of the electron configurations, all right? We simply just add an electron to an orbital that has an available space. And if there's already an electron in the orbital that you're adding the electron to, then that electron must be spinning in the opposite direction as predicted by Hund's rule. Okay, and then some statements here concerning the Aufbau principle. Elements in which the orbital is being filled in the Aufbau process are either S or P of the outermost shell. They're called the main group elements, right? So basically any atom or any element where in the structure, the electronic structure, the highest energy electrons are occupying either the S or P orbitals, then those are main group elements, which are also called the A group elements, right? And just a statement here about the first 20 elements. These are all main group elements. And then we have what we call the transition elements, where as you go from one element to the next, the electron is added to an inner principal shell. All right, we're going to see how that works out. So for example, if you look at the fourth period of a transition elements, the n equal 4 shell is the highest energy shell, but the electrons are added to the 3D subshells. And we're going to see why that is so here, all right? So if you look at the series here, right? So we're starting from scandium, which has 21 electrons. And if you were to go through the same process, you'll see that the electron configuration of argon would be a part of the electron configuration of scandium, right? So that would be 18 electrons. Did I say 20? Hold on. That would be 18 electrons, right? Plus 2 here in the 4s sublevel, and then 1 electron in the 3D sublevel. Now, let me just say something here, because in actual fact, this diagram has the incorrect order of the 3D and 4s sublevel. And let me explain what I mean by going back to a previous slide. So let me go back to this slide here. You'll notice, as I said before, you follow the order or you follow the arrows from tail to head to get the order of the orbitals. And you'll notice that when you get to the 3p sublevel, you'll find that the 4s sublevel here is higher in energy compared to the 3p sublevel, all right? And then after the 4s sublevel, you have the 3d sublevel, right? So it turns out that the 3d sublevel is higher in energy compared to the 4s sublevel. So let me go back to this slide here again. So basically, the 4s sublevel should be before the 3d sublevel, right? Not only in terms of the boxes here, but also in terms of the condensed or the abbreviated electron configuration. So it should be 4s2, 3d1. That would be the correct order, all right? So please make a note of it. In fact, let me just use this arrow here. These two should be switching places. And the same is true for these two here, right? Right, the 4s comes before the 3d, all right? So that's why when you're adding the electrons to the atoms, the 4s orbitals are filled first, and then the remaining electron will go into the 3d sublevel. And then to get from scandium to titanium, you simply add an electron to this to get this. To get from titanium to vanadium, you add an electron to this structure to get this. And then something weird happens when you get to chromium. One would think that to get from vanadium to chromium, all you do is add an electron here. But it turns out that when you add the electron here, that would not be the most stable configuration for chromium. It turns out, and there's, I won't go into the reasons why, but it was discovered by experiments that the actual stable ground state configuration of chromium is where one of these electrons goes here, and this electron remains here. So you're going to end up with this configuration here, all right? Where each orbital between the 3D and the 4s sublevel are singly occupied, right? And basically that observation can be summarized in this statement right here. Completely filled, which we're going to see later on, and half filled, which is what we're discussing now, sublevels are, it turns out, are more energetically favorable configurations, all right? So basically what they're saying here is that if you can have a situation where the sublevels are half filled for both the 3D and the 4s sublevel, that is more stable, or that would be the most stable configuration for chromium. And then to go from chromium to manganese, you add an electron to the 4s orbital. And then to go from manganese to iron, you add an electron to any one of these 5d orbitals. So the electron is added here. And then from iron to cobalt, you add an electron here. From cobalt to nickel, you add an electron to this orbital. And then another weird thing happens when you get to copper. When you get to copper, not only do you add an electron to this vacant orbital to get this, but one of these electrons here, or let me just circle, this electron will go here, and you're going to end up with this electronic configuration, right? And in this case, you'll notice that the 3d sublevel is completely filled and the 4s sublevel is half filled, all right? And it turns out that that is also the most stable configuration in this particular case. So when it comes to the building up of the atoms, or the Aufbau principle being applied to the atoms in the transition region, you have to be careful when you get to chromium and copper in terms of determining the correct electron configuration. To get from copper to zinc is very simple. You simply add one electron to the vacant space here in the 4s sublevel, and you end up with the electron configuration of zinc, which is shown here. So basically, that's how the electrons are arranged for the different elements in the 4th period. And if you understand this, then you should be able to do the same exercise for the 5th and 6th period, all right? Okay, let me see here. So basically, as a result of what we have discussed here, you can basically represent the outer electron configurations for the different atoms, and you'll see that a certain pattern emerges in terms of how the configurations relate to the element's position in the periodic table. Okay, let me first define what is called a valence shell. As stated here, the valence shell is the outermost occupied shell, and it turns out that the period number represents the principal quantum number of the electrons in the valence shell, right? So the periods, of course, go left to right. So period 1 starts with hydrogen, ends with helium, and then we have period 2, period 3, 4, 5, and so on. And what you'll notice is that in each case, let's take, for example, period 3. In each case, the electron, the valence electrons, or the electrons in the valence shell, well, let me put it this way. The 3rd shell will be the valence shell for those atoms in period 3, right? So as we said before, the period number is basically the principal quantum number of the valence shell. So if you look across from sodium all the way to argon, you see that as you go from one to the other, an electron is added to the 3rd shell. And you see the same pattern emerging for all the other periods. Basically, the period number would be equal to the shell to which electrons are added to as you go from one atom to the next across that period. Okay, another thing we need to talk about is that for the main group elements, all right, what you'll find is that the number of electrons in the valence shell is the same as the group number for that particular, the group number for those elements, right? So for example, I'm just going to choose an arbitrary A group element, group 4A. If you look at each of these, right? I don't know if you can see it here, but if you look at each of these, you'll notice that there's a total of 4 electrons in the valence shell for the elements in group 4A, all right? The same is true for group 7A, for all the groups which ends with A in terms of their group number, 1A, 2A, all the way to 8A, all right? So, and this only applies to the A group elements. It does not apply to the transition elements, all right? So, and that's because things are a bit more complicated, as we saw earlier when it comes to determining the electron configuration of the atoms in those elements, all right? Okay, so as a result of what we have discussed here, we can have the elements in the periodic table categorized as belonging to certain what we call blocks, right? So the elements in group 1A and 2A are called the S block elements, and that's because in each case, the number of the electrons in the valence shell would occupy the S orbital of that valence shell. And then we have the P block elements, which means that the electrons in the valence shell will occupy the p orbitals of the valence shell. In terms of the d block elements, basically as you go from one electron to the next, you're adding an electron to a d orbital. And then when you get to the inner transition elements, as you go from one element to the next, you're adding an electron to the f orbital. So these are called the f block elements, all right? So that's basically another way of categorizing the different elements within the periodic table. Okay, so with that out of the way, we can now talk about the difference between the valence electrons and what we call the core electrons, all right? So we know what the valence electrons are. Those are electrons that are in the highest energy level or in the principal, the shell with the highest principal quantum number, right? Those are called the valence electrons. Now, any other electrons that are in the atom, well, before we get to that, so in the case of sulfur, this is the electronic configuration of sulfur, and you'll notice that sulfur has 4 + 2, 6 electrons in the highest shell, highest energy shell, which is the third shell. So those are called the valence electrons, which are circled here, all right? So those are the valence electrons for sulfur. Now, any other electrons within the atom are called the core electrons, right? Those are in the inner shells, right? So going back to the sulfur example, we already identified the 6 valence electrons. That means that the other electrons that are present are called the core electrons. So in the case of sulfur, there are 10 core electrons, 6 valence electrons. So therefore, the total number of electrons in sulfur, in the sulfur atom is 16, all right? So it's very important, especially when it comes to determining the type of ions being formed. It's very important that you're able to make a distinction between the inner core electrons and the shell and the valence shell electrons. Okay, so now we're going to talk about the electron configuration of ions. We talked about the electron configuration of atoms already. When it comes to ions, it's a bit different because we know that if you go from an atom to an ion, the atom would have to either lose or gain electrons. If the atom gains electrons, then we have the formation of negatively charged ions, which are known as anions, all right? So as stated here, anions are formed when electrons are gained to complete a valence shell. So we're going to look at chlorine as an example. So this is a full electron configuration of chlorine, all right? Chlorine has 17 electrons, and you'll notice that in the 3p subshell right here, one of the orbitals is singly occupied. So when you add an electron to the chlorine atom to form the chloride ion, that electron will simply go into this subshell spinning in the opposite direction. So therefore, and it's not shown here, so let me just draw the diagram here for you. So the electron that is added will go here, all right? So therefore, this would represent the full electron configuration of chlorine. So if I were to write it down using the SPDF notation, for the atom, it's 1s2, 2s2, 2p6, 3s2, 3p6. In the case of the chloride ion, it's going to be, I'm sorry, this should be 3p5. My bad. This should be 3p. Let me erase this here. Sorry. Eraser. Okay, go back to this. Okay, so this should be 3p5. And then down here, this would be 1s2, 2s2, 2p6, 3s2, 3p6, all right? So that would be the electronic configuration of the chloride ion formed from the chlorine atom. And this is basically what you do in order to determine the electronic configuration of a monatomic ion. You simply add the requisite number of electrons to the atom electronic configuration, and whatever results would be the electronic configuration of the chloride or of the particular anion that you're trying to draw. Now, when it comes to electronic configuration of cations, you'd have to do the opposite. You'd have to make sure that you remove an electron or remove electrons to obtain a complete valence shell. And this is for the group A elements, right? We're going to get the transition elements later on, but for the group A elements, such as an example of which is sodium here, this would be the full electronic configuration of sodium, right? So to get from the sodium atom to the sodium ion, you'd have to lose an electron. So you're going to lose an electron here, and the result would be this configuration here, all right? So the configuration of the sodium atom if you were to use the SPDF notation, would be 1s2, 2s2, 2p6, 3s1. But in the case of the sodium cation, it would be 1s2, 2s2, 2p6, and that's it, right? There's no electron here, which means that the 3s orbital does not exist. So therefore, this would be the electronic configuration for the sodium cation, all right? Now, what I just described here is in the case of, as I said before, an A group element. Now, things are a bit tricky when it comes to the transition element. Let me see here. What example I'm going to use? I'm going to use, let me use iron 2+. Okay, so I'm going to use Fe2+ as an example, right? Now the electron, let me see here, the atomic number of iron is, let me look it up here. The atomic number of iron is 26, right? So I'm going to write down the electronic configuration of iron here, Fe, right? So it's 26 electrons, right? So 1s2, 2s2, 2p6, 3s2, 3p6, which is 18, and 4s2, and then 3d6, all right? So that would be the electronic configuration, that would be the full electronic configuration of iron. Now, and this is for the atom. Now, if I were to write down the electronic configuration of Fe2+, right? That means that I would have to subtract 2 electrons from the iron atom. Now, here's the thing. You have to remember where to remove the electrons from. And that is what this statement here is all about. Cations formed from transition metals lose electrons from the highest principal energy level. In other words, in the case of iron, the electrons to be lost would be the electrons from the 4s orbital here. And you might be wondering, why don't we remove the electrons from here? Well, it's because of what this statement is saying, right? You remove the electrons from the highest principal energy level, which is the 4th energy level, not the 3rd energy level, all right? So therefore, when those 2 electrons are lost, this 4s orbital would disappear. So therefore, the electronic configuration of the Fe2+ would be 1s2, 2s2, 2p6, 3s2, 3d6. So this would be the electronic configuration of the Fe2+ cation, right? We remove the 2 electrons from the 4s sublevel because the 4s comes from the energy level, which has the highest principal quantum number, all right? So therefore, you remove these 2 electrons here, that 4th shell would disappear, and therefore you just write down what is left, all right? Now, if we want to write down the electronic configuration of Fe3+, all we have to do now is remove an electron from here, from the 3d subshell, right? Because that is the highest energy subshell. So therefore, the resulting electron configuration for the Fe3+ ion would be 1s2, 2s2, 2p6, 3s2, and 3d6. And that would be the electronic configuration of the iron 3+ ion. So when it comes to determining the electron configuration of transition elements, you have to be careful, right? The key thing you need to remember is that the electrons to be removed initially would be the electrons from the highest shell, highest energy shell. And of those electrons in the highest energy shell, you remove electrons from the highest energy sublevel, all right, or subshell, all right? So that's basically what you have to do to determine or to draw or write down the electronic configuration of transition elements, the ions of transition elements, all right? Okay, so let's move on now to magnetic properties that are displayed by atoms. And in this context, there are 3 main types of magnetic properties. excuse me. The first one is diamagnetism. And as stated here, that's a weak repulsion associated with paired electrons. Then we have paramagnetism, which is the attraction associated with unpaired electrons. And then we have ferromagnetism, which is the exceptionally strong attractions of a magnetic field for iron and a few other substances. So what this is referring to is the effect of a magnetic field on these elements based on the electronic structure. Now, the one that we'll be focused on in this discussion would be paramagnetism, all right? What you'll find is that if your electronic structure has any unpaired electron, then it will display paramagnetism, which will be the attraction that this element or that particular element will have for a magnetic field. Now, what I have to show you here is a YouTube video. Let me get out of this here. Okay, so this is a URL for that YouTube video. And this YouTube video basically is showing you how paramagnetism is determined for any substance. All right, so let me copy this here. And let me see here, okay, okay, there's still one person here. Mr. Tanner, can you hear me?
Yes.
Okay, I'm about to play this video. I don't know if you can hear it. I'm going to try and see. I may, well, let me play it first. Could you hear that?
I can't hear anything.
Okay, all right. What I'm going to do is plug in my speakers and turn it up. So,
okay.
All right, so let me do this. Let me restart this. Hold on.
Lake Theater presents Gold Guts, no baloney.
Just science.
Could you hear that?
Yes, sir.
All right, let me continue playing it.
Hi, I'm Joanna.
And I'm Steve.
And this is a test tube of liquid nitrogen.
And this is a test tube of liquid oxygen.
Let's see what happens when we pour the liquids past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So, when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Hey,
Ooh.
more. There's the good one.
Okay, I'm just going to stop there because from there to the end of the video, they're just playing around. So that basically what you see there. Let me plug that my mic in. Okay. Okay, so basically this is the experiment that you can use to determine whether or not a particular substance is paramagnetic. So in this particular case, oxygen has been determined to be paramagnetic because it's attracted to the field, whereas nitrogen just falls right through, and therefore it is determined not to be paramagnetic, all right? Okay, so I just thought I should show you that to show you how they determine whether or not a particular substance is paramagnetic. Okay, so that's basically all that we have to say as far as paramagnetism is concerned. So the next thing we're going to talk about, which is another consequence of determining the electron configuration of atoms, what we're looking at in this section is the periodic properties of the elements, all right? And when we're talking about the periodic properties, we're talking about how the properties vary for the different elements as you go across a period and down a group. So there is a periodic law which states that certain sets of physical and chemical properties recur at regular intervals when the elements are arranged according to their increasing atomic number, all right? So there are certain properties that we're going to look at in this chapter. We're going to see how this relates to the atomic, to the properties, to the electronic configuration, that's what I meant to say, for the different elements, all right? So first thing we're going to talk about is the atomic size, and there are different ways of measuring the atomic size. The way that we're going to use is the distance between the nuclei of two atoms. So if you have two atoms of a diatomic molecule, basically the distance between the two nuclei here is basically what we will consider to be the atomic radii or radius of the atom. Okay, so if we use that definition, then we see a certain trend as you go down a group and across a period. As you go down a group, and this is true for any group, what you'll find is that generally speaking, in most cases, you'll find that the atomic radius increases, all right? So if you take, for example, group 1, which starts with lithium and ends with cesium, and this is a table, or I should say a graph, which plots the atomic radius versus the atomic number for the different elements. What you'll find is that as you go from lithium to sodium to potassium to rubidium to cesium, there is an increase in the size of the atom, all right? Now, another trend that is observed is across a period. As you go from right to left of any period, what you'll find is that the atomic radius increases, or if you go from left to right, the atomic radius decreases. So if you take, for example, period 2, which starts with lithium and ends with fluorine over here, and that's a plot that you see right here. You see that there is, as you go from left to right of that period, you see that the size of the atom decreases as you go from left to right. And the same is true for the second period. The same is true for the third period. There's a bit of a exception at this point right here, but generally speaking, there's a decrease in the atomic radius, and you see a similar general decrease for periods 4 and 5, all right? So that's basically the general trend that is observed for atoms and their atomic sizes as measured by the atomic radius as you go down a group and left to right of any period, all right? Now, we talked about the atomic radius. Let's talk about the ionic radius, all right? Now, the ionic radius, of course, is in reference to ions, not atoms. And the definition of the ionic radius is given right here. The ionic radius of each ion is the portion of the distance between the nuclei occupied by that ion. And this is assuming, of course, it's combined with the other counter ions. So in the case of magnesium oxide, which is shown here, and of course, you know, scientists have their instruments that is used to measure these things. And you'll see that the magnesium ion has a radius of about 65 picometers, and the radius of the oxide ion is 140 picometers. And just to remind you what a picometer is, 1 picometer is equal to 10 to the minus 12 meters, all right? So that gives you an idea as to the relationship between the picometer and the meter unit, all right? So we can understand certain trends when it comes to ionic radii as well, based on what we were talking about with respect to electron configuration. Now, first thing we're going to mention here or talk about is the relative size of the cations compared to the atoms from which they're formed, all right? And what you're going to see here is that the size of the cations would be smaller compared to the atoms from which they're formed. And we can explain that because when a cation is formed from an atom, basically that results from the atom losing electrons, and therefore the positively charged nucleus will attract the remaining electrons more strongly, right? And therefore pull the electrons closer to the nucleus, and therefore the size of the resulting cation would be smaller compared to the size of the atom from which it is formed. So therefore the magnesium ion would be smaller in size compared to the magnesium atom. The sodium ion would be smaller compared to the size of the sodium atom, and so on and so forth, all right? When it comes to anions, the opposite is true, right? What you'll find is that the anions will be larger in size compared to the atoms from which they're formed, right? And the reason why is because when you add electrons to an atom, you're increasing repulsion between the atoms, or between the electrons, I should say, and therefore what will happen is that the anion size will swell up to be larger compared to the atoms from which they're formed, right? So what you'll find is that the oxide ion, for example, I'll write it down here, the oxide ion would be larger in size compared to the oxygen atom, and the chloride ion would be larger in size compared to the chlorine atom, for example, right? So therefore, oxide, or I should say anions, are larger in size compared to the atoms from which they're formed, and the cations are small in size compared to the atoms from which they're formed, all right? So that's another trend that you need to be aware of. Let's talk about this term, isoelectronic configurations. What do we mean by that? Well, basically that means any structures, different structures that have the same number of electrons. We're going to talk about it with respect to atoms and ions, but this can also apply to molecules and polyatomic ions as well, but we won't get into that discussion. Okay, so when you see a series of isoelectronic structures, what you'll find is that the greater the nuclear charge, the smaller would be the size of that particular ion or atom, all right? So for example, if you look at, in fact, let me take this out here. What am I doing? If you look at the magnesium, right, magnesium ion compared to the sodium ion, what you'll find is that the magnesium ion will have a smaller size compared to the sodium ion. Why is that so? Well, because in the nucleus, right here, the nucleus of each of them, the magnesium ion will have 12 protons, while the sodium ion will have 11 protons, but the number of electrons will be the same, right? The magnesium and the sodium ion will have the same number of electrons, but the number of protons will be different in each case. So what does that mean? That means that in the case of the magnesium ion, because you have 12 protons here, they will have a greater pull on the surrounding 10 electrons, right? And therefore they will pull the electrons closer to the nucleus and therefore reduce the size of the nucleus compared to the sodium ion, which has only 11 protons in its nucleus, all right? So that explains why, and these are both isoelectronic because they have the same number of electrons, right? So let me write here, isoelectronic, all right? Right, so basically if you have a series of isoelectronic species, then what you look at to determine which has the greater or smaller size is the number of protons. The greater the number of protons, if the number of electrons are the same, then the smaller would be the size of the particular species or structure. Okay, so let me skip this here. So based on what we have just discussed here, we can understand this table here. Now, this table is basically a version of the periodic table, which shows you the atomic sizes of atoms and ions for the different elements. And what we discussed earlier can be observed in this table. So let me just say first, all these numbers that you see here refers to the atomic size or ionic size in terms of picometers, the radius, all right? So if you remember, we said as you go from left to right of any period, the atomic size decreases. You can see that in each case here, if you take the first period, you see that for the lithium atom, the atomic size is 152. The next element is 111, and it steadily decreases to 71 for the fluorine. And the same is true for all the periods. And then if you look at the groups, we said that the atomic size increases as you go from top to bottom of any group. That's true for any group, 1A, 2A, and so on. And then if you look at comparing the size of the ions to the atoms, you'll see that the ions, when it comes to the cations, will be smaller compared to the atom from which they're formed. So for example, in the case of, let's say sodium, right? Sodium, the ionic size is 186 picometers. For the sodium ion, it's 99 picometers. So therefore, there's almost a 50% decrease in the size of the ion as you go from, as you go from the atom to the ion. And you see a similar trend for magnesium, for aluminum, for potassium, calcium, gallium, all these ions that are formed from atoms, you see that their sizes are smaller. And then the opposite is true for the anions, which are larger compared to the size of the atoms from which they're formed. So for example, if you compare the nitride ion to the nitrogen atom, you see that the nitrogen atom has a size of 75 picometers, while the ion has a size of 171 picometers. So the nitride ion is more than double the size of the nitrogen atom. And you see a similar trend for oxygen, fluorine, sulfur, chlorine, bromine, selenium, arsenic, no, not arsenic, I'm sorry, phosphorus, and so on and so forth. So those are the trends that you'll observe when it comes to the sizes of atoms and the sizes of ions compared to the atoms from which they are formed, all right? Okay, let me see here. I think this may be the last topic we'll talk about today. The other property here we're going to discuss is ionization energy. So first we have to define what we mean by this term ionization energy. It is the energy required to remove an electron from a ground state atom in its gaseous state. So we're talking about a situation like this, all right? Where you have the atom, and to remove an electron from the atom will result in the formation of the ion. So the energy for this process is called the ionization energy, right? And of course, we know that you have atoms which has more than one electron. So therefore, you can remove the first electron, which would be the energy required for that would be the first ionization energy, as you can see here. And then to remove the second electron, we call the ionization energy is called the second ionization energy, and so on and so forth. So in the case of boron, there are 5 electrons to be removed. So basically, these are the values of the ionization energies required to remove each electron, all right? One trend you'll observe here is that it becomes, well, how should I put this? As you remove one electron and then the next one, more energy is required, right? So in the case of the first step here where one electron is removed, this is the amount of energy required. To remove the second electron, there's an increase. To remove the third electron, a further increase, and so on and so forth, right? And we can understand the reason why this happens, because to remove, well, it requires a certain amount of electron to remove the first, or it requires a certain amount of energy, I'm sorry, to remove the first electron, all right? Because of course, the nucleus will have a hold on the electron, so therefore energy is required to remove the first electron. So you end up with an ion, a cation, which has a positive charge, and to remove the next electron from something with a positive charge requires even more energy, right? Because now you're removing something negative from something positive. So therefore, that's why you see the energy increase for the removal of the second electron, and then it increases to remove the third electron for pretty much the same reason, and that continues until you remove all the electrons, all right? So that's basically what explains that increase. Another thing you'll notice is that the increase of energy as you go from the first to third ionization is a bit gradual, and then there's a big jump to remove the fourth electron, right? Now, one might be wondering why that is. And if you look at the electronic structure of boron, let me write it here, that is 1s2, boron has 5 electrons, so it's 1s2, 2s2, 2p3, all right? So we have the first shell here, and then we have the second shell, which has the 2 sets of 2 subshells, S and P subshells. So basically, to remove the first 2 electrons here, hold on, let me see here. The first 3 electrons, I should say. To remove the first, hold on. This is wrong. It should be 5 electrons. So this should be 1 right here, not 3. My bad. Okay. So to remove the first 3 electrons, we require removing the 3 electrons here from the second shell. All right. So therefore, to remove the first electron here, second electron here, third electron requires these amounts of energies. So, you know, it's a gradual increase, relatively speaking. Then we have to remove the other 2 electrons, we have to go to the shell, which is much closer to the nucleus. And therefore, that's the reason why there's a big jump when you get to the 4th electron being removed here. When you compare this to this, you see that there's a big difference. And then when you compare this to this, there's, well, not a relative, not as big a jump as in the case from going from the 3rd to 4th electron. And that's because you're removing between these 2 here, this one and this one, you're removing the 2 electrons here, which are closer to the nucleus. So we can understand how the ionization energy trends for one atom varies based on the electron configuration of the atom, all right, based on the arrangement in the shells and the subshells. Okay, if you're talking about the first ionization energies for atoms, then these are the trends that we would observe, right? Going across a period from left to right, the ionization energy increases for any period. Now, there are some exceptions, and we're going to talk about those exceptions, maybe not now, but definitely next class, right? So as you can see here, there's a plot here of atomic number versus ionization energy that is cut off here, but that's what the y-axis is all about. So the first element here is hydrogen, and then the next element is helium. So there's an increase in first ionization energy as you go from hydrogen to helium, right? And then lithium, which is in the second period, its energy is down here. And then to remove an electron from the next element, which is beryllium, more energy is required, right? And then as you go from beryllium to boron, there's a slight drop here as you go from beryllium to boron for the next first ionization energy. And let me try to explain why that happens. So the electron configuration of beryllium is 1s2, 2s1, and the electron configuration of boron is 1s2, 2s2, all right? Now, in the case of beryllium, for the first ionization energy, you're removing this 1 electron from the s orbital. However, in the case of boron, you're removing one of these 2 electrons from the s orbital. So the question now becomes, why is it that the first ionization energy of boron is less than the first ionization energy of beryllium? And the answer is that because these 2 electrons here in the 2s sublevel, they're occupying the same orbital, right? And there's some repulsive force between those 2 electrons. So because of the repulsive forces between these 2 electrons, it is easier for this electron to be removed from the 2s orbital of boron compared to the 1s electron in the case of beryllium, right? So because of the repulsion that exists between the 2 electrons sharing the same 2s orbital, less energy is required to remove one of these 2 electrons from that structure. And therefore, that's the reason why you have this dip here in the trend from boron to beryllium. So this is, let me try to squeeze this in here. That's boron here, and this here is beryllium. All right, so that explains why we have that dip in the electronic configuration from boron to beryllium. Okay, I think I'm going to stop here. Let me just check. So yeah, I'm going to stop here for today. Let me just say that I'm going to post an assignment in Canvas, and if I'm not mistaken, it's going to cover chapters. I think I already gave you an assignment which covered chapter 5. So 6 and 7 will be the chapters that will be covered by the next assignment. I think that is assignment 4. So look out for that. I hope to post that later on this evening. All right. Any questions before I leave?
No, sir.
Okay, all right. All right, so that's basically it for today. So I see you on Thursday. So take care. Enjoy the rest of your day.
You too.